you have any questions, then I can answer, and then also the other question.
Yes, sir. There are many questions, sir.
Yeah, so let me just...
Can I read out for you?
Yeah, that is better, in fact, I think.
Okay.
I think I have already talked about is the rate function related to large deviation function.
Yeah,
yes.
Related to...
Yeah.
That's the first question. Then the next is how these large functions are important in physical systems.
Yeah, so I guess...
from because thus.
Yeah, okay. So I guess this question was asked probably before, I guess, this slide, I guess. So I think I have already talked about it because...
okay, then
yeah, basically, like when you go to the small systems, this large fluctuation becomes important. And nowadays, because of the technological advancement, you can actually go and probe small systems. And to probe small systems, you need to understand what is the nature of large fluctuation. For example, one of the systems might be this gravitational. You have heard about these gravitational wave detectors, and then so these are the detectors. They need very precision measurement, and you use very small parts. And in this kind of systems, it's very important to understand. I mean, how does the fluctuation affect those systems? Basically? Yeah.
Yes, sir. Thank you, sir. The next question is there any physical meaning of partition function? And one more request, those theoretical things you are explaining, there should be some real life examples as well, and asked by Vaswajyoti Borua, sir.
Okay, so 1 minute, let me just go to this thing. Yeah, is there any physical meaning of partition function? Yeah, and one more request, those theoretical things are explaining, there should be one more real life example of... Okay.
Example as well.
Okay, so let me just give you one more example. I guess if you can tell me, Vaswajyoti Borua, if you can ask me about again, what do you mean by those theoretical things? Did you mean the large deviation? Then I can give another example of large deviation. Or can you refresh the question? Maybe I was not sure what is the...
Bhaskar Kumar Das says, write something, sir.
Okay.
Fluctuations are important to understand the phase transition phenomena. Thus, the large fluctuations are also implied some kind of phase transition phenomena.
No. Okay. So I understand the question. Okay. Let me just... Okay, so can you see? Yeah. Okay. So when I talk about large fluctuation, there are two kinds of large fluctuation we are talking about. Okay. So one is, of course, so if you take a equilibrium system, okay. For example, you take a gas and then you take a gas volume of gas. It's a large volume. Okay. Large volume of gas, and you change the temperature of the gas. Okay, you reduce the temperature of the gas, and at some point the gas will become liquid. You reduce the temperature, and liquid will become solid. Okay, so this is the phase transition, and at the phase transition, at the second order phase transition, there are huge fluctuations in the system. Okay? For example, correlation function diverges. Okay, so this is one kind of fluctuations. So these are the fluctuations even in large systems. But there is another kind of fluctuations. So the fluctuations, even if you are away from the phase transition, this is just in the gaseous phase, let's say, and measure the density, there will be density fluctuations. So these are the fluctuations I am talking about. So those fluctuations are negligible for large systems. So those fluctuations are of order 1 over the square root of the volume. But if I go to a small volume, because the fluctuations, so this is away from phase transition. So fluctuation goes like 1 by square root of the volume or number of particles. So for large volume, for thermodynamic system, this is quite small. But if I go to small systems, right? So this becomes, becomes not so small, and that becomes relevant. For example, if you take one colloidal particle in water, you can still describe using statistical mechanics, but in this case, these fluctuations becomes important, right? For example, if you want to describe molecular motors inside your body, right? They are just moving in this microtubule, so their thermal fluctuations are important. So in that case, it's important to describe large fluctuation, and those large fluctuations are given by large deviation function. Okay. So these large fluctuations are nothing to do with the large fluctuation you see at the phase transition. Okay. So the phase transitions are still basically described by whatever the Landau theory or whatever it is. Okay. So I think there was another part of the question. What was the
question?
Yeah.
Is Maxwell's domain violating second law of
okay.
thermodynamics?
Okay. Yeah. So okay. Before that, there's this. Okay. There's this thing, partition function. Is there any physical meaning of the partition function? Okay. So I guess. Okay, the way partition function arrived is basically that's the normalization constant. But now, given this partition function, as you see that you can actually define this free energy. So in that case, in that sense, there's a physical meaning. So log of the partition function has a physical meaning. That's the free energy. And given this free energy, basically you can compute everything else. Okay, I think I hope that answers this question. Okay. Is Maxwell-Demon violating second law of thermodynamics? Yeah, okay. So this is again a word actually. When you say violation of second law of thermodynamics, so what is the meaning of violation of second law of thermodynamics? Okay, so that is essentially, I guess, just go back to this one. So this is what, as I said here, let's just look at this thing. So second law says that heat always flows from the hot reservoir to the cold reservoir by itself if you do not do anything, right? For your refrigerator, that's why you need to do something else. You need to put energy from outside to extract heat from the cold place, right? So anything against this, anything apart from this, you just call it as violation of second law, right? And so for example, in this system, so this thing also you can just call it a violation of second law, but it's just a term. It doesn't mean anything physically. So one should not take it very seriously when somebody says that violation of second law. So second laws are basically for macroscopic system, and in macroscopic system, heat always flows, for example, from the hot reservoir to the cold reservoir. And in this kind of systems, so like for example, what is the probability of heat flowing from the cold reservoir to the hot reservoir? This is also termed as a second law violating event, but this is just a term, okay? And similarly, Maxwell-Demon, there's a way to resolve this Maxwell-Demon by constructing something, putting information into the system, and but I'll not go into it. But it's basically it doesn't violate second law of thermodynamics basically. So there's a way to resolve this, and but these are just the words actually. So it doesn't mean much. Okay. Yeah. So is there any?
Yes, sir. Then
please explain
if Sita Upasana asked about explain what is the use of the theorem in biophysics field.
Okay. Okay, so there are various part of this theorem actually. So I didn't go into detail, but okay. So let me just go to this there. Okay, so one of the theorem, it says basically that uh, okay. So what I saw is that there is something called entropy. So I have defined this entropy, and then I said that okay, this entropy is a stochastic quantity, and it's basically it has a distribution. So for example, if you plot the entropy, okay, so this is a positive side. So typically it will be like some positive this thing, but there will also be some. So let me just. Okay. So what it says, okay, it will probably also have some negative part and there will be some positive part. This is a typical one. And it's important to know what are the events which violates this entropy, violates the second law. Again, I am just putting a jargon, but it basically says that what are the events which not doesn't produce entropy, instead it consumes entropy. And there's a theorem which is called the fluctuation theorem, which says that okay, probability density of entropy of some taking some value small s divided by probability density of entropy taking some value less is exponential of minus s by kb. And so what it means that basically, so knowing the entropy production on this side, because these are the things it's easy to measure, so you have an idea of the events which are consuming entropy. Similarly, okay, you can similarly when people also try to do it for the heat and work, for example, okay, for example, you might write down a similar curve for, so this is for entropy. Similarly, you can write down a, for example, so it's a minus some kind of beta times, okay, sorry, some w times some kind of kbt. And it says that, okay, if you take a distribution of the work, as I said earlier, so if you know the distribution of the work here, you can make an estimate of the distribution of the work here. So these theorems basically give a way to estimate fluctuations of rare events. There are also other relations called Jarzynski relations. So where, I mean, given the work done along a given trajectory, if you measure it several times, knowing that you can basically measure the free energy difference. So okay, there's another relation which says, okay, exponential of minus, okay, beta w is equal to exponential of minus beta times delta free energy between some point to some other point. So where if you start with an equilibrium system at some this thing, and then you do some non-equilibrium process, and then you go to some other point. For example, you can just think of it like you have a system in a harmonic trap, and you just it's in equilibrium, and then you have just changed the trap of the strength of the trap. So system goes from one equilibrium state to another equilibrium state, and you can measure what is the work done along this path. So this path will be different because this is a stochastic path, and then you can measure this work done for various paths and then take the expectation value of this exponential of minus beta w. And what you can show is that it's basically the exponential of beta times the difference between the free energies in this. So therefore, measuring this quantity gives another way of measuring this free energy in equilibrium systems. Yeah. So, okay, these are few of the examples, okay, in the biosystems. For example, you can just think of this, pulling this RNA and okay, folding DNA or whatever protein folding. So what is the energy cost for this whole kind of system? Yeah. So it's just basically one way to understand this fluctuation in small systems, basically. When a system is said to be a good thermodynamical system, okay, so system is a good, okay, so a system is a good thermodynamical system when it's large, I guess. I mean, it's a large system in equilibrium. It's a thermodynamical system. No, I mean like a glass of water. That's a good thermodynamical system, right? So any system, so okay, so what is a thermodynamical system? So this is a system, so usually suppose you take a glass of water. So how are you going to describe this glass of water? So if you want to describe this glass of water from microscopic, there are 10 to the power 23 water molecules there, of the order of 10 to the water molecules there. Each of these particles are molecules are basically going on its own. There's some interaction between them, but they are essentially following Newton's second law. Right? At that, so if you want to describe this system from Newton's second law, you have to write down equations for 10 to the power 23 particles and describe. It's a huge task. It's impossible to do that. Okay. Instead of that, what you choose to do, you choose to describe the system in terms of some physically relevant quantities. So what are the physically relevant quantity for a glass of water? Just the temperature of the water, volume of the water, pressure of the water, right? So those kind of systems where basically you just describe with few physical quantities are the thermodynamic systems. So a glass of water is a good thermodynamic system. Yeah. Does it answer the question? Yeah. Bino Chetri, yeah. Does it answer the question? Okay. Why is small system? Why small system? Why does heat for cold is upper? So okay, maybe. So this heat flow is okay. One way of saying it. Okay, let me just give it another example. So these are all equivalent examples. So let's take your. So that's what I was telling you. So let's take a big volume in your room. So these are gas inside the room everywhere. So what is the probability that you see this thing goes to a state where all the gas particles are here and you are just standing here, right? So this is a big system. So you don't see these kind of events, okay? But now if you keep going to small systems, let's say a system of 2 particles, okay? Let's just consider a system of 2 particles. Let's consider a system of 2 particles, okay? There's a finite probability that all these 2 particles are on this side. No? Okay. So this is like okay. So I mean, what is the probability? It's just a 2 particle, which just a half to the power 2. Right? With 1/4 probability, both the particles will be on this side, right? Or there, okay, 3. Depending on if you divide by 3, this 2 factorial, it's a different thing. But okay, there's a finite probability that there are 2 particles on one side. Okay. Similarly, when you go to small systems, so what is a heat bath? So you have this guy. So what is how do you model these small systems? So this model this small system. So what you have is, so this is your hot bath. This is your red bath, right? This is your hot bath. And this is your cold bath. Okay. So now, how are you modeling? So you are connecting the system to this side and other side by some system. Okay, so you have a system like that. Okay, suppose your system is something like that, right? And this is connected to the heat bath. This is connected to the heat bath, and in between it's not connected to the heat bath. Now all these water molecules are hitting this guy. All these water molecules are hitting this guy. And that's how the bath is basically putting force into the system, which is the heat, or energy into the system, which is the heat. Because these events are random and these are small system, once in a while there might be fluctuation there. This guy is putting more heat into the system than this guy. In that case, heat will basically go from this side to the other side, right? So because the fluctuations are important, the energy scale we are looking at, the energy scale of the system is of order kBT, right? So kBT is the temperature scale. So anytime if you're looking at a system whose energy scales are of order kBT, fluctuations are important and anything can happen. I mean, anything you do not expect by the second law of thermodynamics. Does it explain? Okay. What is the importance of observing deviations of the system? I think it's the same. I guess I have said already that, okay, with large fluctuations is important for small system, and that is one way of characterizing this basically, right? Okay.
Then from Sir Ayush Hazarika,
okay,
we have assumed that the system is under a time paradigm which is flowing from past to future. If the arrow of time is reversed, the time is flowing backward. Then will the equation be same or there will be some changes?
Okay, so it's a very good question actually. Okay, so what is the arrow of time? Okay, so it's a very important question. So let me just okay. So when you say the equations, so which equations? Okay, so the fundamental equations which describe the systems are the Newton's law. Right? It just says that basically m dvi dt is just the force I. This force can be, and this is for all I. So this force can come from external force, interaction with other particle, and anything else. Okay. So these equations are Newton's, and then you need one more equation which says that, okay, dxi the equation governing this is said, okay, dxi dt is just the velocity, and dvi dt is just the force. Okay. So this is basically a Hamiltonian system. Okay. So these equations are time reversible. So that's why when I say that, so these equations are time reversible. That's why when I say that there's a finite probability of going to a state. So suppose you start with a state where all the gas particles are here. Soon you will go to a state where it's equally distributed. Since these equations are time reversible, so you can also find a state where you suppose you start with a configuration where all the velocities are reversed. So then you'll go back to a state which is this. And in equilibrium, all the states have same probability, right? So therefore, there is a finite. So any state any configuration has the same probability in microcanonical ensemble, not the one I have described. So therefore, there will be a configuration where all the velocities are reversed, and then you will basically go to a state which is like that. So this is called the time reversibility. But now this is something we do not see in our nature. So all the equations governing the macroscopic objects are time irreversible. Okay, so this time reversibility is lost at some point, and this is what basically describe this. Okay, I mean gives the arrow of time. So I do not know at what tech level I can go, but okay. So what you can do. Okay. So to describe this system, so what you write down is that, so you write down this system in the phase space. So in the phase space, so you describe the system by phase space density. And this system in the phase space evolved by something called Liouville equation. Okay. So Liouville equation is time reversible again, because Liouville equation is basically describe the bunch of trajectories which is governed by this Hamilton's equation, Hamiltonian system. Okay. So now you go through several assumptions, several time scale separation, etc. And then at some point you arrive at something called the Boltzmann equation. And in this Boltzmann equation, the assumption you make it that so whenever two particles collide your system, I mean collide means when they come within their interaction zone, and then they again go away. By the time they come back again, it takes a long time. And therefore, before and within that time, they might have collided with several other particles. So therefore, within that time, basically, they have lost all correlations. So you assume that this particle before collision, they are uncorrelated. This is something called molecular chaos hypothesis. And this is basically a place where your time reversibility is lost. Okay. So another way of looking at this loss of time reversibility is basically, okay, so this is where time irreversibility arises. And so maybe, and of course this one, okay, when you write down this equation, and then when you come to the level of this equation is already time irreversible because you already have a frictional time. So when you model the bath, basically you have already put this time irreversibility in the system. So although you have started with your Hamilton's equations inside this particle, but at some point basically you have gone to a coarse-grained picture where you basically, instead of looking at all water molecules, how they are heating, and then what is the force they're going, you have gone to a coarse-grained scale. And at that scale, basically, you have lost your time reversibility. I think, does it, I don't know, does it answer the question?
Then, sir, another question is, does the dissipative systems always deal in non-equilibrium statistical mechanics and stochastic thermodynamics? Asked again by Vikas Kumar Das, sir.
Does the dissipative systems always deal in non-equilibrium?
Non-equilibrium
Statistical mechanics. Okay. See, non-equilibrium statistical. Okay, so let me just maybe I'll just go back to this slide. I think that will be important. I think useful. Okay. Okay. So as I said, this as opposed to equilibrium systems, the non-equilibrium systems are given by dynamics. Okay. So this dynamics can be at several stages. So this need not be the dynamics at the microscopic scale. I mean, that dynamics, it can be some kind of effective dynamics. And how do you describe this dynamics, for example? So imagine that you have a system, I mean, we have this configuration. So this configuration is basically, okay, the way to describe the system where the system can belong, okay? So the system moves from one configuration to another configuration by some stochastic rules. So once you give me these rules, you give me the dynamics. So as I said, this is now for a particular kind of systems where, let's say the system, when it moves from this configuration to other configuration, it doesn't depend where were it before coming to C1, okay? So this kind of processes are called Markov processes. And these Markov processes, given you give me these rules means basically you give me these probabilities. of jumping from one configuration to the another configuration. So I can write down an equation how the probabilities evolve. So for example, probability of being in a configuration C can be any one of these configuration. So what is this? So that means that if it was at C, before that it was in some other configuration. So what is the probability of that? So it was in some configuration C prime. So C prime is any configuration other than C. And then there's a probability of going from C prime to C in a small time delta t. So this is the probability. So therefore, this W is called the probability rate, okay, because this is the probability per unit time. Okay. So this term says that how you come into the configuration C. So there is also another probability that you were already in configuration C and you did not move anywhere. So what is that probability? So that probability is that, okay, what is the probability that you move somewhere? So this is basically that sum of all probabilities going out of C. So this is WC to C prime dt, sum over all C prime. Then 1 minus this is basically the probability that you stay at C. So it's probability that you stay at C, and then this is the probability that you did not move. Okay, so that's the equation. And when you take delta t going to 0 limit, so you see that, okay, you can just take this guy on the left hand side divided by delta C, and you arrive with this equation. So this equation is called the master equation. And similarly, you have a Fokker-Planck equation when this configuration space becomes continuous. For example, your colloidal particle, for example, the configuration space is continuous. It's a position, a continuous variable. The equivalent equation is called the Fokker-Planck equation. So depending on the system, dissipation is not, okay, so it's basically something, okay, it's not always easy to define something what is dissipation, but it's, so the non-equilibrium system, the better way to describe non-equilibrium system is that, okay, so this given this equation, so this equation is in fact true for equilibrium system also. But what is the difference between equilibrium system and a non-equilibrium system? So the difference between is that, let me just write down this equation and somewhere. So the difference is that, okay, so I have written down this equation dp dt of C. This is C prime not equal to C. It says that, okay, P of C prime W C prime to C minus P of C W C to C. So that is the same equation I have written down, not equal to. Yeah. So now, if you start with some initial state and let it evolve by this equation. For some systems, it will go to a steady state. Steady state means that the probability doesn't change with time. After a long time, when t goes to infinity, for some systems, not everything, for some systems, dp dt will become 0. So it means that P of Ct goes to a stationary distribution which doesn't depend on time. So at that case, the equation it will satisfy is that the same, but now stationary state. So these are all functions of time. These were functions of time, but now time is not there. C prime W C prime to C minus P stationary state C W C to C prime. Okay. So this is equal to 0. Okay? That's how you define the stationary state. Now you can get this 0 many ways, right? Because it says that the sum is 0. Out of many ways, there is only one specific way. So this doesn't happen to everything. So that depends on what are your W's are. So one specific way, one case is that each of these terms are 0. It says that between any configuration, C and C prime, you have bidirectional arrows, right? in non-equilibrium, in general, you need not have arrow in both directions. And you say that P steady state of C prime, W C prime to C equal to P steady state of C, W C to C prime. This is called detailed balance. And when the system has detailed balance, then it basically gives rise to equilibrium state. So the equilibrium has detailed balance, and all the other cases, when it doesn't satisfy detailed balance, when the rates do not satisfy detailed balance, what state you will get is basically non-equilibrium state. It might be steady state or not steady state, depending on the system, but it's a non-equilibrium system. I do not know. Does it answer the question?
Yes, sir. Then, sir, another question from Bhim Prasad Sharma. Does a fermionic system behave differently from a system when the large deviation is considered? Again, what does a system consisting of paramagnetic molecules? Sir.
Does a fermionic system behave differently from a bosonic system when large deviation is considered? Yeah, so now again you have to tell me, see, large deviation is again basically, okay, you are asking for small system. Now you might ask, okay, if you have a 2 fermion and a 2 boson, how different are they? For example, between fermion and boson, only thing is that they cannot occupy the same state. But so if you are, now it depends on at what temperature you are, but okay, I mean, they are different. I mean, there are systems where actually, yeah, okay, okay, so let me just answer this in a different ways. Okay, so so there are systems where people actually look at, so another kind of problems where, I mean, people look at these fermionic systems, for example, you can ask, so suppose you put n fermions in an harmonic potential, right? They are non-interacting fermions, you put in a harmonic potential. And then you can ask what is the, you just look at in one dimension, you have n fermions in a harmonic potential. So these energy levels are basically like equidistant energy level, n plus half h equals omega. But since this, you cannot put 2 fermions in the same state, to write down this configuration, you have to basically, although they are non-interacting, so you have to write down in terms of the Slater determinant, right? So you write down that, and then you can ask, okay, what is the probability that your rightmost fermion, what is the probability of finding the rightmost fermion? So there is a probability, you can associate a probability with that, and so these are called extreme value events. Actually, you look at the large. So this kind of system also has this large division form, and if you look at for the fermionic system, this will be different from, for example, if you look at for a bosonic system, because bosonic system, everybody will be at 0 temperature, everybody will be at the center, but fermionic system, there'll be a huge spread basically. So yeah, even if you look at large division, there'll be a difference between fermionic system and bosonic system. So it depends on what kind of question you are looking at. Okay. So there, I mean, people, actually one of my collaborators also, he looks at this fermionic system, let's say largest eigenvalues of a fermionic system, or what is the farthest position of the of a group collection of fermionic systems, and you get interesting behavior basically. Yeah. Yeah.
So last one is, why probability theory always related to large deviation principle?
Okay, that's a very good question actually.
That's the actually last question, sir.
Okay, so let me, okay, that's a very good question. So I did not tell you how this large deviation function error. I mean, how did we get this large deviation function? Okay, so maybe let me just. Okay, let me how to go back. Okay, so maybe actually no, forget about this one. I just explain. Okay. So take a sum of random variables s equal to sum over xi I equal to 1 to n. Okay. So these variables are called IID random variables. That means these are independently drawn. They are independent. They are not related to each other. And drawn from the same distribution, from the identical distribution. They are drawn from some distribution Q of x. Right? And you're asking, what is the sum of this random variable P of S? So what is this distribution? So this is what you are asking. Right? So for that, for simplicity, just assume that, okay, this random variable, this is 0, and okay, the variance is just given by 1. You can put anything. Okay. So then you see that your S is simply 1 to n xi. This is 0, and S square, since they are uncorrelated, it will be just 1 to n xi square. This is, each of them are 1, so this is n. Right? So these are typical variance, typical fluctuations are square root of n. So now you can ask, what is the distribution of S? Okay. So it says that, so the central limit theorem says, so this is, okay, I'm not going to derive what is central limit theorem. Says that this object, since the typical fluctuations are of square root of n, so if you divide it by square root of n, so if you look at this object, so this is still a random variable, and in the limit n going to infinity, P of y is given by the Gaussian distribution. So this is where the universal Gaussian distribution come from. So Gaussian distribution is universal as long as you have a finite mean and a finite variance. Now you can ask, okay, so this variable y describes the square root of n fluctuations. But I might be interested in the fluctuation of order n. I can look at another variable which describes the fluctuations of order n. And you can show that, now again, I am not going to show, okay, that this one, in the limit n going to infinity, okay, it has a form depends on n, so it goes to 0 exponentially n, times some function of z. Okay. So this function I of z is non-universal, okay, but this form is universal. Okay. So now why does this form appear in these problems I have talked about? Let's go back to this problem of this density of gas inside a room, right, inside a small volume. So how do you measure the density of gas in a small volume? So this is your now, okay, this is your big volume, and then this was your small volume V. Let's just enlarge this small volume V, and this small volume V you can again divide into smaller volumes of delta V. So let's make this volume so small that only one particle can be there. Okay. So now what is the number of particles in this small volume n. This is just the number of particle, sum of the number of particle within each volume, and this one is either 0 if no particle, or 1 if particle. So what is the probability that you do not find any particle? So P of equal to 0. What is the probability that you find one particle? Right? That means what is the probability that this is equal to 1? So that is just the density times the volume, right? Because these are independently you are putting this particle. What is the probability that it's equal to 0? This is 1 minus. Right? Right? So therefore, this number of particle, again, you can write it as a sum of random variables, which now in this case takes value 0 and 1, whose probabilities are given by this one. Right? So this is where this large deviation function comes. Basically, whenever you write some variable as a sum of random variables, that variable has a large deviation form. Like for example, this example I have given when I was computing work in a given amount of time, I have integrated over time for a given duration. And this integration is basically, you can just think of it as a sum, right? So in this case, it was m, and in this case, that was a sum over t, basically. So that's why this, instead of n, this t. So it says that, okay, this guy says that in this case, p of n will have a large division form times some n times some quality, or so v times some. Okay. So this is where this large division function is related to this probability theory. Yeah. Yeah. Okay.
Okay, sir.
Yeah.
Then, sir, here we end the interaction session.
Okay, there's I think another one.
Yeah, another one, but.
Okay, I think yeah.
Would
Yeah, as I
like
said that, okay, I mean, yeah, so I think as I said that, okay, in general, it's difficult to describe non-equilibrium system, and for different system, you have to basically find a way. So there's no general formalism. For Markov systems, you can write down something like that. Yeah. Okay.
Okay, sir. Thank you for your response, sir. Yeah.
Okay, thank you.
And sir, this is the end of the part of our seminar and the webinar section. And now I request Rajan Datta from the Department of Physics, Lakhimpur Girls College, to give the vote of thanks. And over to Rajan Datta. Thank you.
Good afternoon to all of you. Myself Rajan Datta, on behalf of Department of Physics of Lakhimpur Girls College, offer my sincere gratitude to our esteemed resource person, Dr. Sanjib Sabhapandit, Professor 1 of Raman Research Institute, for delivering a most valuable lecture on the topic, large deviation in non-equilibrium system, and also for an amusing and fruitful interaction session. I think this is one of the longest one. I am sure that all of the participants learn a lot from the esteemed resource person. I hope that in the future course of time, our participants and students would be benefited from that institute where Dr. Pandit working as Professor 1. It is also my privilege to let you know that Dr. Sabhapandit is from our district Lakhimpur. In fact, his residence is just adjacent to our college campus. It is such a pleasant experience that Dr. Sabhapandit immediately gave him his consent for this webinar without any further delay in a situation like this pandemic. So I am again grateful to him. On behalf of the Department of Physics, I offer my thanks to our principal, Dr. Surajit Bhuiyan, for taking all the initiatives and encouragement for holding this webinar series in this critical phase of time. The most indispensable part of this webinar series is the participants all over the state and abroad. Without their active participation, this webinar might be useless one. On behalf of the department, we offer our heartiest thanks to all of you. I offer my thanks to organizer of this webinar series of physics department, particularly our HOD, Mrs. Binita Hazarika, and other faculty members. At last but not least, I would like to offer my heartfelt thanks to Dr. Parama Datta, perhaps the youngest faculty of our college, for looking after all the technical pros and cons of the webinar, without which we might not be able to make it a successful one. With that vote of thanks, we are concluding today's session. Thanking you all from the family of Lakhimpur Girls College. Thank you all.
Thank you, everyone. Give it now.
I think you feel exhausted.
Okay.